Welcome students. So we are discussing about the design of asymptotic observer, which is also known as Leuenberger observer, because Leuenberger has invented this observer. So in his name this observer is given, a name is given, that is Leuenberger observer. So we have realized what is the need of the observer. Need of observer is that we have realized that to implement the state feedback control law we require the information of states, means all the states are available for the measurement to implement the state feedback control law. But in reality it has been observed that not all the states are available for measurement for different reason. So to implement the state feedback control law, one can design an observer which is asymptotically accurate, means it will estimate the states of the plant with the help of output and the input to the plant. With that it is also a dynamical system. Observer is also a dynamical system, but it is not the physical system. It can be implemented in a algorithm, or it can be implemented in a computer which is producing the estimated state x hat. And our aim is to design the observer in such a way that the difference between the true state and estimated state must goes to zero as t tends to infinity. Okay, so in this regard we have discussed that mainly there will be two methods are there. One is called open loop estimator, but about the open loop estimator we have realized that the error dynamics, because our aim is to develop a mechanism by which the error, that is the difference between the true state and the estimated state, must go to zero as t tends to infinity. If we want to ensure for the open loop estimator, we are observing that the dynamics of the estimation error are fixed by the eigenvalues of A and cannot be modified. Okay, so we cannot modify the eigenvalues of A, and the convergence of error depending on the eigenvalues of A. Okay, so this method is not a good method for estimation. So then we have added with this open loop estimator. So for the open loop estimator, the observer equation is x hat dot is equal to a x hat dot plus b into ut. So here actually we are not utilizing the difference between the output of the system and the difference between the output of the dummy system. So what we did, we have taken the difference of the output of the original system and the output of the dummy system, and we have added with the dynamical equation of the observer, that is a into x hat dot plus b into ut plus l into c into et. And after that we have observed, so this scheme is known as Leuenberger observer. Okay, so here you are finding that we require the information of ut and we require the information of yt. This ut and yt, which is this yt is the output of the original system and ut is the input is given to the system. So if you assume that this is a dynamical process which a b c are known to us, with this a b c we will build a observer where the same input has been given to the observer, and the output of the system is compared with the output of the observer, and it is multiplied with the suitable gain, and it is given or it is feedback. Okay, so this is the scheme of the observer with the dynamical process. So now we can assume that this x hat t will be produced by the observer will be close to the true state. And it has been proved also that the error dynamics, if we found out that error dynamics is a minus lc into et, and we are observing that now we can modify the eigenvalues of A, means we can choose a proper gain L by which we can place the eigenvalues of A minus AC at the left half of the S plane, and we able to place the all the eigenvalues of A minus LC at the left half of the S plane. Then we can guarantee that that if for any initial condition this error is going to be 0 as t tends to infinity. Okay, and we have proved that this is possible, this placement is possible only when, if we will assume that only when it is possible if the SCA pair is observable. Okay, now what we will do, we will just discuss with an example how we will compute this gain gain L for state observer design. Okay, or asymptotic observer design. If you have a low order system, that is, if you assume that you have a system whose order is less than equal to 3, and if you want to design the observer, full order observer for that system, full order observer means if the order of the system is 3, you want to design an observer order of 3 because you want to observe the 3 state of the system. Okay, so then first step, you have to check the observability. If you know that the system is observable, then we can define the observer gain L, that is L1 L2 L3 transpose. As I told you that L matrix will be a column matrix, so its dimension will be 3 cross 1. Okay, and substitute this gain and in the desired characteristics polynomial, because if we have a error system E dot equal to A minus LC, and if we want to place the poles of A minus LC at the left half of the S plane, then the characteristics equation for this error system will be Si minus A plus LC. Okay, so you calculate in terms of L1 L2 L3 what is the characteristics equation of error system, that is Si minus A minus LC. Okay, now if you determine that where you want to place the poles of the observer, that is mu1 mu2 mu3, that we have to, the designer has to decide that where the pole has to be located. And as I told you that first criteria to place the poles of an observer is that all the pole must be located at the left half of the S plane, and then another requirement is that it must be placed in such a way that its response will be faster compared to the controller, because controller is going to use the information produced by the observer. So that's why there must not be any delay in the information, because if there is any delay in the information, then the controller which is using this delayed information may destabilize the system. Okay, so now if we have decided that we have to place the poles of the error dynamics at mu1 mu2 and mu3, then we can calculate what would be the corresponding desired characteristics equation. Okay, and then solve the gain elements by equating the like power on both sides, this Si minus A minus LC, and you equate with S cube alpha 1 S square plus alpha 2 S plus alpha 3, and you can calculate what will be L1 L2 L3. This procedure has been shown with a very special form which is called observer canonical form. Okay, so suppose we have a system which is in observer canonical form. Okay, so this is the A matrix, this is the B matrix, and this is the C matrix, and this matrix for this system we want to estimate the state x1 x2 and x3. Okay, so we suppose we have assumed that all the states are not available for measurement. Here you are observing that y equal to x1, it means that only x1 is available for measurement, x2 x3 is not available for measurement. So we want to estimate the x1 x2 x3, all these three. So this is called full order observer. Okay, so now if we want to compute A minus LC, and where the A is L1 L2 L3, then it is very easy to calculate, and this will be the matrix A minus LC. And if we want to calculate the characteristics equation of A minus LC, that is also very easy to calculate, because it will be S cube plus A1 L1 S cube plus A2 L2 S plus A3 L3. Okay, and if we know the where the pole has to be placed, that is mu1 mu2 mu3, we know SQ alpha 1 square plus alpha 2 s plus alpha 3. Then what we will do, we will compare these two characteristics equation to get the values of L1, L2 and L3. It is very similar to the controller design what we have already discussed. So now directly you can design, that is called method. Another method is called for higher order system you can use this method, that is method 2. It is based on the transformation technique. Okay, suppose we have the characteristics equation with A matrix Si minus A, and we will identify the A1, A2, An minus An. Okay, once it is known, you can compute the M matrix by picking the elements of An minus 1, A1 1, An minus 2, like that. You have seen in case of transformation matrix we build for the controller canonical form and the observer canonical form. Okay, then if the mu1 mu2 mu n are here, it will be mu n. If the mu1 mu2 mu n are known, then we can compute the desired characteristics equation. Then alpha 1 alpha 2 alpha n are known. You see A1 A2 An alpha 1 alpha 2 alpha n is known. Then we can build this matrix alpha n An alpha n minus 1 An minus 1 like alpha 1 A1. Then to compute L, what you have to do, you have to take the inverse of the product of MO, where O is the observability matrix. So you can use this formula directly to compute the gain of the observer. So this is the method 2, and you can also use the Accustomed formula, that L equal to phi of A, where into the observability matrix inverse into 0 0 0 0 1 depending on the what is the order you are using. And this phi A is the characteristics equation, desired characteristics equation with A matrix. So this is the three method by which you can compute the gain L. Okay, now another important thing is known as separation principle, but in details I am not going to discuss that one. But this block diagram is important, where observer as well as the controller is used together. You see, this is the dynamical system, x dot equal to ax plus bu, which is producing x, which is multiplied with the c, we are getting y. So now for this system we have assumed that not all the state variables are measurable, but we have to implement the state feedback control law. Then what we will do, we will design an observer. So this part is the observer part. So here observer equation is x hat dot equal to a x hat dot plus b into u plus l into v, where v is actually y minus y hat. So how this observer has to be built, u is required, so you can tap the u, and you require the information of y minus y hat. So how we will get, now this observer is going to produce the estimated state x hat. So now x hat is multiplied with the C matrix to get y hat, and from the original system we are, or the true system, we are getting y. So we will compare, we will get y minus y hat, which is given to the observer. Now this observer is going to produce x hat, and this x hat can be used for the controller, because we know that state feedback controller require the information of state. So here instead of true state we are giving it observed state, and this observed state is multiplied with the suitable gain, and which is used for the feedback. So this is the total scheme for the observer controller configuration. So here the questions come, when the observer and controller is working together, then the K and L, these two matrices, means these two gains, we are choosing correspondingly for the system and for the observer. So can we choose this K and L independently or not? It can be, by mathematically it can be shown that there is no interference between the observer design and the controller design. We can make it independently and then we can have together, but basic rules and regulations for the controller design and the observer design has to be obeyed. Okay. So here one numerical example has been given. Suppose x dot equal to ax plus bu, y equal to cx. Okay, so now we will see the observability test CCA, rank of CCA. We are finding 2, so it is observable, and we want to place the poles of the observer at -3 -4. What is the meaning of we want to place the poles of the observer at -3 -4? It means that we want to place the poles of the observer error dynamics at -3 -4, and for that we want to calculate what will be the gain. So that's why we will calculate the desired characteristics polynomial, that is s plus 3 into s plus 4, and also we will calculate the characteristics polynomial of si minus a minus lc, and by si minus a minus lc, and we are getting this expression. Now if you compare this expression and this expression, you can compute what will be the values of L1 and L2. So here we are getting L1 is 4 and L2 is 2.33. So this is the gain of the observer, which ensures that the poles of the observer error dynamics will be located at -3 -4, and which guarantees that error of the system, means error of the observer, is going to be 0 as t tends to infinity. It means that the estimated state is going to follow the true state as t tends to infinity. So this example has been simulated here. First we have simulated the open loop estimator. When we have used the open loop estimator, at that time we have assumed that this LV term is 0, means this is not there, and it is 0 means there is no use of this y minus y hat, and we have assumed that the open loop estimator is x hat dot is equal to a x dot plus bu, and it has been observed that if you see, these solid lines are the true x1 and true x2, these solid lines, but this dotted line is the estimation. So now you see there is no agreement between the true state and the estimated state, and if you compute the x1 minus x and x2 minus x1 minus x hat and x2 minus x hat, this is the error plot. You see none of the error is going to 0. So open loop estimator error converges to 0, but very slowly. You see maybe after 4 seconds it is going to obey, but there are significant amount of error is there. But if you use the closed loop estimator, means if you use the equation, that is, this is the observer equation you will use, that is x hat dot equal to ax dot plus bu plus l into v. If you use, then you will find that both the states, that estimated states, are converging to the true state, and error is becoming 0 almost after 1 second. So there is a convergence of the error to the 0 as t tends to infinity. So this observer is working fine. So now final thoughts. Note that the feedback gain, means the observer gain, basically in the estimator only stabilizes the estimation error. If the system is unstable, then the state estimates will also go to infinity with 0 error from the actual state, because if you estimate the state of an unstable system, then unstable system, you know that the states may go to infinity. So observer states also will estimate that states which is going to infinity, but with a 0 error. Okay, estimation is an important concept of its own, because not always just part of the control system, means it is not like that always you have to use the estimation for the control purpose. Independently, for the guidance and navigation also, you will find that the estimation is important, and estimation is all about which do you trust more, your measurements or your model, because you are finding that here to build the observer you have to depend on the model information A, B, C. These 3 things, if it is not known, then this Luenberger observer is not it is not possible to implement. Okay, and also you have to trust on your measurement that you are tapping the y from the original system. If your y, means the error, your measurement is corrupted by noise, then what will happen? This system may not work, means this Luenberger's observer may not work. So you will find that from here the new theories have been started, that if the system is corrupted by noise and also the measurement is also corrupted by noise, then in that situation how you will do the estimation? and for that the Kalman filtering is there, and these are the modern as well as the more advanced concept which is not required for you. So these are the references we have used. So this is the end of your observer design. So now maybe I will float one small assignment based on observer. So it is very easy to understand because it is similar to the controller design, but you have to be cautious what is the difference between observer design and the controller design. Okay, so as well as this is your end of the course, and I hope that this E mode of learning you have enjoyed, and also I'm thankful to all of you because you kept your patience for so long time, because you know that these slides were not prepared from the beginning. In this lockdown period I have to prepare this many of slides, I have to type it, and then I have to frame the questions because no material is with me now. During the lockdown period I am trapped in my home, so all the notes are with means it is in NIT Shilchar, so everything I have to organize, and then I have to prepare the slides, then I have to record it. Okay, so it that's why it has taken long time. Anyway, it is good thing that you have responded also in a very good way, because you have solved all the problems of the assignment nicely. I'm very happy with that. Okay, so at the end note, what I want to tell that if you feel that any portion you are not able to understand, then definitely we can discuss through telephonic conversation or through WhatsApp, whatever the mode you prefer. And definitely when we will meet, and I hope that meeting is coming soon, that we can meet very soon, and then face to face interaction we can do. Okay, so thank you once again to all of you.